So I'm sure there will be a couple more people coming, but I guess let's start. First a brief recollection of what we did the other days. So we finally defined what the Courant algebroid is. So it was this tuple of data, vector bundle, a bracket for the space of sections of that vector bundle, a fiberwise pairing, and a vector bundle map. And it's subject to a bunch of axioms, so Jacobi, or Jacobi. This property, so this is for all sections and all functions on the base. So that's some derivative property using the anchor map. The bracket preserves the pairing, and then there is this prescribed form for this for the symmetric part of the bracket. And we proved, based on these axioms, some small propositions. One of them was that one gets a natural associated complex using the anchor map and the dual of the anchor map. And we call the Courant algebroid exact if this was exact. And we called it transitive if this map was surjective. So if rho was surjective. And then we discussed an example, and we proved some classification theorem. The example was essentially this one. We called it the exact Courant algebroid associated to a manifold M and the closed tree form H. And it had this form, so that was as a vector bundle, it was the direct sum of T and T star. Pairing and anchor are natural, and I mean the obvious things, and the bracket took this form with the tree form included in here. And then we proved a couple of things. So we proved a proposition. We prove a proposition which says that there exists a isomorphism covering identity M between two such guys over the same base. If and only if they were cohomologous. They differ by two form. I mean, sorry, by a d over two form. Okay. And then we showed that actually every exact Courant algebroid is of this form, which was this classification theorem. It says that every exact Courant algebroid is of the form eta and h for some h. And we showed also, and then we are putting these two things together. We know that we see that exact Courant algebroids over M are classified by distance by the third Generalised homology of M. Okay, so what do we do today? So first recall, so that's done. Maybe let me make a sneaky definition just because today or later. So the exact Courant algebroid with 0 3 form, so the one that we started actually the whole business with, will be called standard Courant algebroid. And I will denote it, just to simplify the notation, by this double T. Because it's T and T star. Obvious. Yes. Okay, and then so we won't really need anything else beyond the fact that actually we will need the following little thing. So how does this theorem proven? So so in the proof of the theorem, so what we did was that we started with some except algebroid. We picked an isotropic splitting of that sequence. So we showed that this existed globally. So we showed that you can always pick a splitting, isotropic splitting, which means this just splitting means that if you post-compose it with the anchor, you get the identity. And isotropic means that image of tau actually Lagrangian. You said Lagrangian. So image of tau was Lagrangian. Okay, so we picked this thing and then we used some. Then there were some further steps, but essentially what we used this for is that we identified. So this led to the following map, which was simply tau plus the dual of the anchor map. Okay. And we showed that this was actually an isomorphism. And this showed that as vector bundles we have this isomorphism, and then we kind of looked at what does the possible bracket look like that we can build it there, and then kind of concluded the whole thing. But one thing I want to point out is that so if you look at this, forget about that. So if you look at this example here, then there is a nice way how you can kind of extract H from here. So if you know that you have if you are given this example, then note that if you take a bracket of two vector fields and then you pair it with the third one, then this precisely gives you H, X, Y, Z. Okay, because this guy gives you the vector part and the one-form part, and pairing it with the vector only keeps the one-form part. So this one, so we get precisely that thing. Now, consequently here, from the way we constructed this, you can see, or easily believe me, that here. Okay, so one step back. So we showed that taking the Lagrangian splitting, we get an identification like this, and using this identification, we can transport the Courant algebra structure to some Courant algebra here, which has precisely this form for some tree form. Now, how do we recover the tree form? We use this thing and the Lagrangian splitting. Okay, so the claim, well, look at the claim. It kind of follows that the resulting tree form is given by so if we started with this guy, then we can recover the tree form like this. If we start with with an abstract Courant algebra, then we need to identify this, so we need to use the splitting. So this is what I'm doing. Okay, because this tau is the thing that identifies kind of okay, whatever. This is the result. I mean, if you trace this map back and this identification how it went, then you should easily see that the corresponding tree form you get from this Lagrangian splitting is given by this in terms of the Lagrangian splitting. This is some tree form. Now, well, obviously there was in doing this there was this was the end of the proof. Now, looking back at the proof, you see that there was a choice here. So there was a choice that we need to pick at the beginning, and that was a choice of a Lagrangian splitting. So we knew before that, we showed before that this exists, but it's by no means unique. So what does happen if you choose a different Lagrangian splitting? Well, you should still get an exact Courant algebroid with some tree form, but it should be the isomorphic to the previous one. So by proposition, you know that it needs to be related by d of some tree form. So let's check that explicitly. Okay, so is this okay? Hold on, the question. So what happens if I change the Lagrangian splitting, or if I choose a different one? Okay, what age do I get? Is the strategy clear? I mean, this was maybe anyway. This was kind of just a tie of the thing from before. So picking the Lagrangian splitting, you did this identification with ECA of this form, and to discover precisely what age you get, you use this formula. And now we are checking what happens if you change the splitting. Okay, so what happens? So suppose. Okay, so this is the question. Answer. So suppose tau and tau prime are two Lagrangian splittings. Then what we do as before, so we use tau of I mean both of these guys, sorry, tau and tau prime, they go from Tm to the Courant algebroids. Now we can use tau to identify E with this Tm plus T star. Okay, so well, by the above construction. So what I want to say is that it kind of now so we use this to identify, and from now on we just work here. Okay, so I don't work with abstract Courant algebroids, I work with ones which I have identified. So now the question is, okay, so so I have this Tm plus T star m, where I use tau to construct it, and now I'm asking, okay, so this tau prime is another Lagrangian splitting. Okay, so this okay, so I use first one to identify the T plus T star, and then I just start Lagrangian splitting in this special case. I mean, in this case. And so what do I get? So first of all, we know that. Okay, so since this is splitting, we know that the image of that L prime has zero intersection with the cotangent bundle. I mean, if something would land in the cotangent bundle, then then composing with the anchor we would kill it, but we want that to be the identity. Okay, so it has this property, which means that it's a graph. So image of tau prime is a graph of some two form. Graph of B, where B is a two form. Okay, so this we showed before. So now we already have, we have candidate for what this two form might be. I will call it the same letter. But let's check now. So how do we check? So what is the three form H? What we call it H prime, corresponding to tau prime. Well, I use that formula. So H prime x over z is tau prime x, tau prime y, tau prime z. And now we just substitute. I know that it's a graph, so So what do I have here? So I have x plus insertion into B, and I have y plus insertion into B, and then I have z plus insertion to the insertion of z into B. So let's calculate using this formula. Okay, so we have a vector. First part gives me Lx y plus Lx I y b. Then I have minus I y v I x b. Okay, that's these three guys. But then I also have a three form, which here, so this is now the bracket in this guy where I use tau to construct it. So there is a corresponding h corresponding to the tau. Okay, so this is the one given by tau. And in that I insert the vector bits, so x and y. And then I contract it with this. Okay, and then maybe just some parentheses. So vectors paired with covectors. So how do I do that? Right. So I insert this vector into that form, which is bzb, and then I insert z into this, plus inserting z into first term, minus inserting z into second term, plus inserting z in here, which just means that I get x, y, z. Okay, now hopefully this should assemble into giving a differential, so let's see. Give a second. Let's put IZ at the front. Okay, so I put IZ because there's a contraction into a form, two contractions anti-commute, so I get minus I Lxy. B I will put at the end. And then I get this one. And then I get this one. Into B plus H x. Okay, now let's hope that it assembles. Okay, so what is this? By the formulas, this is a commutator of Lie derivative minus, sorry, Lie derivative and contraction. And first one cancels this thing. And what remains combines, so is it plus I, y, Lie derivative of x. This is precisely 1/2 of that, so we get exactly that this is the other half. So I z, I y, I x into dB and plus h x y z. Okay, this is precisely just dB fed with x and then y and then z. Okay, so from this we can conclude that this h prime is indeed just this h moved shifted by this b. Okay, so well, precisely that thing. Okay, does this make sense?
Okay, so if I understand correctly, based on this, you know that there exists a B, the tuple which is associated with change of splitting. Is it also, can you also see from this that to each two form you can find the splitting such that the
Yes, because so it's easy to see that if you have a splitting, then using the two form, you always get another isotropic splitting. So that's easy to see that it's still that you get that it's still isotropic. And then we know that for any isotropic of Lagrangian in this case, this procedure holds. So we get the Courant algebroid and identification with some exact Courant algebroids of that type. So, but yeah. So the basic fact is that if you have two isotropic things, then you can relate them by two isotropic splittings are related by a closed two form. I will write that actually.
answer your question? Yes. Good. Yeah, thanks.
Is there some formula for B in terms of tau and tau prime? Like, because it's a little bit indirect, no?
Yes.
So, is there some kind of nice expression for it? Or because you have to do two steps, no? You first have to do the identification using tau, and then you have to use the identification between this B
Yeah.
and this.
Okay, true. Maybe, okay, there should be some. Let's see.
Also, it should be kind of anti-symmetric in tau and tau prime. If you exchange them, you should get minus B, because it's a kind of how they differ. You know, like if you do the calculation based on tau or based on tau prime, then you should get something that differs by just
Yes,
psi.
that's true.
And this construction somehow treats them a little bit, you know, asymmetrically.
Yes, very much so. Yes, I agree. I don't think. I mean, maybe I'm wrong. Yeah, I'm. Maybe there should be something easier. But actually, I think you are referring to anything that Frederick said. Let me put it actually as I want it now. That was the original one, which I'm not proving. But yeah. So well, yeah. As you were saying, it's very indirect, like the way I did it. So I'm sorry if there is a better way. But at least okay. So what I did is that I picked one of them, used the identification, and then choose the other one. But what you can show is that this in fact gives you an action. So lemma. So that in particular this gives you a so it's a torsor of the over closed two forms. So lemma is a fixed A Courant exact from algebroid. Then the above assignment, so the thing, the above construction assignment, let's say, where you start with an isotropic splitting. And, okay, let's say a pair, and a two form, and we produce another isotropic splitting. So that's what we've done about. So this in fact gives you an action of the abelian group of two forms. So this is in fact a transitive action of the abelian group omega 2 on M. So group structure is simply adding two forms. And this is an action on the space of isotropic splittings. So although as you said, the thing I did above was kind of very indirect, it shouldn't be difficult to see that just playing with this essentially, without using forgetting about the bracket and everything, just looking at this kind of linear algebraic problem, you should be able to see that, for instance, if I would have three guys, I would have tau prime and tau double prime, then changing the stuff by tau and then changing it, using tau to make the identification, then modifying the splitting using tau prime, and then modifying it again should be the same as modifying by the sum of tau prime plus tau double prime. And that's not like super immediate from here, but it shouldn't be too difficult to check.
And this splitting that we used last week, to prove this theorem, that one was not canonical, no? So if I give you exact Courant algebroid with exactly this freedom,
yeah, it's not canonical. It's definitely not canonical. Yeah.
It's like choice of origin here in this.
Yes.
Space.
Yeah, exactly. So yes, precisely. So there is an abelian group acting on. Yeah, I mean, yeah, it's a torsor, so it's a transitive action of the abelian group of this vector. It's a torsor of this vector space. Okay. Yeah. And it shouldn't be difficult. I'm not proving this, but it should be just playing a little bit with that, and you should be able to find that. Okay, but is at least the statement clear? Good. doing this, what's the reason? Yeah, so I wanted to say something a little bit, maybe, I don't know, maybe this isn't suitable to do it in like a master's course, but so let me put this. So let me call it remark with a star, meaning that if anyone is taking an exam at the end, then this definitely won't be on the exam, because I will. But it's, I mean, it's not difficult. It's just that I don't want to introduce the. This is a remark, advanced remark for those of you who know Czech homology. So it might be fun now. Okay, so. But first, was this kind of construction clear? Okay, good. So now the fun remark. So suppose that one thing we know is that every exact Courant algebroid is locally is isomorphic to this standard one. Do you see why? Why is it locally always the same as WTM? Maybe this is the so exact Courant algebras are classified by circle homology. So if I take it over some small or contractible neighborhood, then there is no circle homology. So they are all the same. I mean, they are all isomorphic. Okay, so the problem comes with like if there is some topology. Okay, so we know that. Okay, so what does it mean? Now let me attempt to draw a picture. So let's say this is our manifold M. And well, and let's suppose that I pick some cover that I don't know. Let's say that all bits are contractible or like small enough. Probably contractible is the word. Okay, so I take a contractible cover. I know it actually. Okay, take a cover U alpha. Such that U alpha and their intersections are contractible. Maybe I don't need the second, but probably need. Okay, so I have a bunch of these open sets, and by the above remark, I know that if I start with some abstracts, there is some big abstract Courant algebroid hanging over. Okay, exactly. This is what I have given. Now, if I take these kind of sufficiently contractible open sets, then I know that over each of these open sets, this guy is actually isomorphic to that thing. Okay, so there is a. I'm not sure how to draw this, but let's say here associated to this open, I have this standard Courant algebroid over that neighborhood. Here I will have another one associated to beta. Okay, and on each of these neighborhoods, on each of these open sets, I can build an isomorphism between this guy and this standard Courant algebroid. Okay, so this is over. This arrow goes over this little open set, and this one goes over the other one. Let's call this thing, I don't know, what do I call it, phi alpha. And here I have a phi beta, and those are isomorphisms. Okay, so this is a Courant algebroid isomorphism between E restricted onto the open set and E restricted, and this one. And here it's an isomorphism between E restricted to this open set and this standard Courant algebroid. Good. Okay. Okay. So for each alpha, I have an isomorphism. E restricted to there, and phi alpha. It's an isomorphism between this guy and this guy, and they are both Courant algebroid over U alpha.
Good. So now what am I going to do with this? So, well, now I look at the intersections. I look at this guy here. So this is U alpha intersection with beta. And I notice that on this intersection, what I can do is I can go around. Okay, so I have some on. So here I again have some standard Courant algebroid. Bless you. And from this Courant algebroid, what I can do, I can go along that map. So I can take like phi alpha inverse, and I can end up with E that was restricted over that, and then I can use the second arrow to come back. So then I use phi beta to go to, well, the same thing. Okay, so I use the fact that on this intersection I can restrict this, either this one or this one, and I can get this standard Courant algebra of the intersection. And I know that I can now go around. I can make a loop, so I can go from there. I can identify this with E, and I can go back here. But because both of these guys are isomorphisms, so now this is an isomorphism. It's a Courant algebroid isomorphism of this special guy of double T of the intersection. But we did a calculation before, and we know what the so in other words, it's an automorphism. So we obtain an automorphism. Okay, so we obtain an isomorphism, an automorphism of that guy, and it's associated to alpha and beta. So we call it B alpha beta. Maybe to emphasize that I'm not taking indices, then let me put this like this. Okay, so I get an automorphism of this Courant algebroid. Okay, and I get such an automorphism at each double intersection. Okay, but these are not any. Okay, so now I have data. So I have data B alpha beta, which live in out phi U alpha beta, and I have these guys for any alpha and beta. And one thing that I know from the construction is that, okay, so I know automatically that having triple intersections, U alpha with U beta, intersection U gamma, I have that if I add those things together, then I get 0. This comes from the construction. And if I draw a more complicated picture still with triple intersections, then I know that if I want to pass from alpha to beta, and then I pass from beta to gamma, and then I pass back from gamma to alpha, then I should get the same thing. So that should translate to that condition. And this is what is called a check turquoise cycle. This means that this collection of B alpha beta is a check. Sorry, one cycle. One cycle. Thank you. Is a one check cycle in for actually sorry, even better. Instead of writing this, I can just say this is a 2 form which is closed. I didn't say that. Sorry, that was the point which we used from the proof before. Is that we know that these guys are precisely closed 2 forms. Over the minimum. Sorry, that thing kind of fell away. Okay, closed because if you use a closed 2 form, then it maps the same page to the same.
Because you are over the identity, you don't have the homomorphisms, right? Because otherwise automorphisms
Yes.
will be different. Same
Yes.
direct product.
That's right. Mm-hmm. Oh yeah, sorry. Yes, so this is an automorphism covering the eigenvalue. Okay.
Yes.
And we call it out in yes. Okay. Right. Thank you. Yeah. So not only we know, it's an automorphism, but it covers the sorry. Yeah. we are talking about isomorphisms covering the identity. Thank you for that thing. Kind of. Okay, I corrected it. Okay. Okay, so to say it again. So restricting here on each overlap, we have an automorphism of this standard Courant algebroid of the intersection, and we know precisely that that's just closed two forms. So on each double intersection, we have a closed two form. So we have a Chekhov cycle for the sheaf of closed two forms. I said this is an advanced remark, so if you don't know what the sheaf is, then don't worry. But anyway, we will cover that maybe next lecture. So this is maybe a little glimpse from the future. But for those of you who know, yeah, this is just I have a collection of these guys for any double intersection, and they satisfy this co-cycle condition. Okay.
Sorry, I don't quite understand why they satisfy the co-cycle condition.
Okay, yeah, I didn't really explain that very well. So yeah, that should mean that so morally, if you have a triple intersection, or if you have a double intersection, so well, this B, you should think of this B as being sort of a kind of, it's a thing that I use to pass from okay, what's the best way to say it? I mean, well, morally, it's something like you use it to pass from alpha to beta, and then you kind of pass from beta to gamma, and then pass back from gamma to alpha. Then if it's zero, okay, then that was probably not very meaningful. But if you want to do it in terms of pictures, then what it should mean is that, okay, let's say that. So here I would have this T U alpha, here I would have this T U beta, okay, T U gamma, and here I have this E, and what this B is.
I mean, we can even, it's enough for me, by the way, if you take the last B to be 0, so it's okay that you just, I didn't understand why they should sum up to 0, even just two of them, right?
No, not two of them. I mean, if you only have alpha and beta, and this would be beta alpha.
Beta gamma, and like the last
one.
You can specialize it.
No. So you see, the thing is that if I start with such a setup, then I create, then this thing, if I make these choices of this phi alpha, so the strategy is, I start with an exact algebroid, and some open cover, and first claim is that I can choose a bunch of these phi alphas. If I choose this bunch of phi alphas, then by doing these kind of compositions, I get a concrete set of B's.
Yeah.
So I don't have a choice in them. I cannot set some of them to 0.
No. I meant that if you pick gamma equal alpha, I guess.
Okay.
The expression, the
Right.
last B alpha will be probably 0.
Yeah. So you're asking, like in the simpler case, why is this thing 0?
Why even that? Yes.
Yeah. So that should be okay. Let's see. So okay. So one of them should be that you go in this direction.
No,
I think
right. Because they compose like, this comes from beta composed with phi alpha minus 1, right? So the B, which has two indices alpha and beta, comes from a composition of phi beta and phi alpha minus inverse. So they factorize kind of. So if you multiply them,
It's true if you look at the green thing, like that's
you
kind of
just follow it and compose the inverses.
Yeah, that's what Ryan says. Now look at the green equation and then build the picture and go from right to left.
You get to identity because you go with the inverse followed with 1 and then,
I guess what's puzzling, which is also puzzling for me at the moment, but I mean, I'm sure it's true, but is this thing that there is a plus here. But I mean, the plus should be the composition of these.
Yeah.
But for Bs you have usual class, no? Bs live in the second, omega 2, so then
Oh,
it's like,
you say it should be alternating for the Checo cycle?
no, because it's cyclic. No, it's
exactly,
Beta,
exactly.
like B beta alpha should be minus B alpha beta. That's that equation.
No, in this cyclic sense,
Yeah, so no, it's a plus.
Yeah, it's fine.
But this is kind of a hidden in the lemma, no? Because the lemma says it's kind of associativity condition
Yes.
that is in the lemma when you say there is transitive action of group. So the fact that if you compose and then act, or if you act 2 times, that's kind of the.
Okay.
And also the inverse. Tauer's question is that there is inverse, no?
Yeah. Okay.
If phi alpha inverse phi beta, then it would be followed by phi beta inverse phi gamma inverse. Yeah.
Okay.
So, or maybe yet a different way. So, like if you look at this triple intersection, where you would have this kind of u alpha, u beta, u gamma, then you have kind of 3 different maps. You have 3 different maps to E over that neighborhood. One of them given by this phi alpha, one of them given by phi beta, and the other one given by phi gamma. And these B's they are like kind of the transition from one to the other.
Yes.
And yeah.
No, intuitively it's clear.
Yeah.
Okay.
Yeah, we can talk about it. Yeah, I'm for some reason I cannot explain it better at the moment. But it's a fair question. Okay. Thanks. Okay. Right. You see that it's truly an advanced remark in the sense that I'm puzzled by the explanation. Okay, anyway, sorry. Okay, why am I doing? Okay, yeah, right. Okay, so then one remaining thing probably everyone anticipates at this point is that okay, so now there was a choice at the beginning, and that was the choice of the phi's, right? So what happens if I take a different choice of phi's? So if I take different instead of phi's, if I take different phi's, then it means that I'm recomposing them with some automorphism on E. Okay, so if instead of phi alpha, I take some other automorphism, and we know that all automorphisms, they have to be the same. Where I put it, okay, or I can recompose this with some stuff. I don't know, some A alpha. So this A alpha is an automorphism. Or maybe I should post compose this. Sorry. Yeah. With an automorphism, and this is an automorphism of this guy. Okay. Any two phi's that I can do, because they are automorphisms, I can just I can take the inverses and I can go here and then I can go back. Oh, sorry, the other direction. I can go. Well, you know what I mean. Okay, so you go back and then you go here and then you get a map from this thing to itself, which is this key. And okay, so now I have a bunch of these A's which live here. This is this is the same as close to forms over U alpha. And you can ask, okay, how does this change the corresponding B's? Well, if you do the calculation, it should come out that this induces the change of B's. Is that the new, kind of the new B come out to be the old B plus maybe put the parentheses here. Or the other way around.
It's co-boundary.
Yes. So this means that B changes. So this is B, which was in the second Checo cycle, changes by a co-boundary. Co-boundary. That's
equation, and this means that what I should look at is the check is the corresponding cohomology theory. So then I should look at the check cohomology, usually denoted like this. This is the first one. This is the first check cycle of M with values in this sheaf of closed two forms. So, right. So given such a thing, I get an element in there, and then well, the final claim is that this is the same as the third cohomology of the manifold, which is easy to show, and I can show that if people are interested. This is kind of like different viewpoint of the classification, a different way to arrive at it, using some fancy machinery. Also Czech is a very important person in this place, I suppose.
Especially.
Yeah.
No, but everywhere.
Yeah, in general, but in particular also here.
Yeah, that's the right place to complain about Czech chronology. If you don't like them, they can be there.
So is it special for the third one, like for the round homology, that you can calculate it like this, or
No,
is
no.
it for any two?
No, it's general.
If I choose any 2 degrees, kind of, right? I write n as n1 plus n2.
I think so.
Because for the complex, I know that if I take like
Right.
n with values in the
Yeah.
It's just this double complex between the round and homology.
Yeah, I mean, I want to. Yeah, okay. I will show you this case, but it will be clear that it works in general.
Jako ty vieš, že potom po schodech hore dolu a mezi tím dostáváš všechno.
Ale
Tak jako si potom vždycky na vždycky.
no, ale to
To je přesně to samé. A tak končí.
Okay, so just to finish this kind of slightly abstract. So I want to show, in the case at hand, that if I calculate this guy, or definition of this is just what we saw before. It stops satisfying cocycle model of boundaries, and I want to calculate this. Okay. And so the way to do that, again, this is for those of you who know about sheaves. Then you probably also know this a lot. So there is this. You can consider the following sequence of sheaves. This is one of them. The other one is to do the same. Omega 1, one closed. Sorry. Omega 1, omega 2 closed. So normally, if you take an open set, then this won't be a short exact sequence. But it is a short exact sequence of sheaves because of the way sheaves work. So for sheaf, the exactness here would mean that if you take an element in here, then you can restrict it to a smaller neighborhood such that it will be in the image of this. So for sheaves, this is okay. And for sheaves, if you take the associated long exact sequence of cohomology, then what do we actually want? Or maybe let's start here. So we want to have something that has the first cohomology and that has this guy. So the associated sequence would look like this, and then of the closed two forms, and then here there would be, sorry, one. Okay, I'm writing the associated long exact sequence. This, and here I would get, so this is the LES, the long exact sequence, and here I would have the second guys, right? Second of this one. This one, etc. But the point is that this is 0 and this is 0 because these are what is called a fine sheaf. So these are because the sheaf omega 1 admits a partition of unity.
So they derive away from the 0.
So the all higher cohomology of those guys is 0. And this shows that this is the same as this one. So we know that this is the same as the other one, when I saw 1 and 2 essentially.
Okay, that shows also in general that you can kind of.
Yeah,
and it's
okay,
how
yeah,
you can reduce it.
yeah, exactly. So then, yeah, use the same one here. Okay, so then I don't need to write it. But yeah, then you use the same trick here and you lower it once more, and you get this is the third cohomology of closed zero forms, which is just R. This is the sheaf of locally constant section.
No,
Locally constant section.
but R is not fine sheaf, no?
R is not a fine sheaf.
So then in this argument we use the fact that those are. Okay, yeah.
No, okay, let me write it down.
Yeah.
So if I write it the same thing here for H2, then I get H2 of this guy, then I get H2 of this guy, omega 0, which is 0, because that's just functions, and that's a fine sheaf again. I can use partition of unity for them, and then this continues with the third.
Okay, let's go.
For R underline, and then there is third for this one, and this
It's
one
also
is
fine.
also fine. So it's also 0.
Okay.
So this shows this one, and this is kind of.
So you can make it actually very explicit. So you take the two form and partition of the unity, and you wedge with d of h alpha, multiply by h beta, and sum over alpha beta, and you get your class, T-class. So there are explicit formulas using partition unity which tells you how you can go in the spectral sequence from there on to and vice versa.
Okay, that's nice. Okay, I see.
So it's just like you know, the mathematician way to do it, but you can have explicit formulas using partitions of unity.
I see.
B partition of unity, and you construct the class of it. H.
Okay, thank you. That's cool. Okay, yeah, and the last one is after we found out that this is the same as the third cohomology of the.
But this is not like completely obvious thing, no? Because the Czech homology would be kind of that you would have constant functions on multiple intersections, and you want to construct out of it like three closed tree forms, so modulo exactly. You know, that's
Right.
to prove the last thing, you kind of need some kind of spectral sequence or this type of. Because the left
Right.
side has constant data, but like on multiple intersections.
Right. Yes, but do you need?
I guess you basically proved that if you go one more step to the left, then you would get the zeroth Czech cohomology with values in omega 3 closed. Now if you went one more step to the left, then that would probably be the right hand side because it's like global sections of.
Oh, you mean here?
Yeah, kind of like that. No, that's probably where you would find the right hand side.
Right.
Taking global sections factor, no, the zeroth Czech cohomology. three forms.
But then, okay, I would have to, okay, yeah, right, I mean, it goes, but then you cannot use this, because there will be no longer zero.
And you also want to get homogeneous with just closed forms.
Right,
You
okay,
know.
that's true. Maybe it will be easier if I would have done it the other way.
No, it's just that the right thing probably sits kind of naturally on the left.
Right.
The run.
Yeah, okay, okay, thank you. Okay, that's, well, anyway, thank you. But, yeah, okay. Okay, okay, yeah, thank you. So, apologies for this. So, okay, but one reason I wanted to mention this, apart from having like different proof of the same thing that we've seen before, is that you can in principle use this kind of, maybe not that, but you can use this kind of approach by check homology if you want to tackle the transitive case. So, but instead of doing that, let me just take the following theorem, which kind of close this classification part. Okay. This is again theorem of algebra, which says that every transitive Courant algebroid is, and now the important word is locally, automorphic to something that starts like that, but then there is another bit which is okay, where G is a Lie algebra with invariant pairing. Okay, and well, maybe before continuing, let me just break this down what this means. So this means that if I take the sections of E and I can identify them with vector fields, plus one forms, plus functions on the base valued in this Lie algebra. Okay, and now let me write the rest of the structure. Okay, so the anchor map. Okay, let's say S. Okay, vector field one form, and this is a G-valued function. This is just X. And pairing. Will be as before, alpha y plus beta x plus the pairing in the Lie algebra. And the brackets. This is the vector part, just as before. T and S, the functions on the base, valued in the Lie algebra, so I can take the Run differential of that. I get one form, valued in the Lie algebra, and then I pair this in the Lie algebra to get a one form. And plus okay, so here I am, these two terms, this is just the action of the vector field on that function. So I take derivative of that. And I put it in parentheses because this is the vector part, this is the one-form part, and this is the Lie algebra valued function.
This B and H is like hidden inside of this Lie algebra in this case.
B
Like
and
literally.
H.
The B, the H, yeah, the
Well, I mean, this is kind of the local case. So this is the case where you would have like
yes.
locally, you remove this thing,
Try to get it away.
get it away.
Okay.
The thing you are asking is the next thing. So
Because H is 3 of B and you twist the bracket by BT.
And then, yeah, so the corresponding statement there would be that that locally, the corresponding local statement of this would be that locally everything is isomorphic to this Tm
Without H.
without any H.
Right, so the Tm bar and this G cross N, so they are like Lie algebroid, right?
Sorry?
It's like a Lie algebroid extended by one form.
Yes. Yes. Okay, so in principle you can use a different strategy than what we than the one that we've seen before. So you can study. This is like your local model. So if you're interested in like what is all possible global, what is the most general global structure of transitive Courant algebra which locally look like this for some G. So if you let's say you fix G, Lie algebra with invariant pairing, and you're asking like what is the most general Courant algebroid that I can build that locally looks like that, then the answer, one answer to that question is that you should study the automorphism group of this thing, and then the thing is the corresponding check. I mean, then you can calculate the corresponding check homology, which might be more advanced here because suddenly it will be some non-abelian stuff in general. So okay, but in principle you can with abstract let's say that the answer is just the check homology. That's the thing that classifies such.
So it would be for abelian, no?
You can do it for non-abelian if you're interested in the first check
First,
homology,
okay,
which is the one there. Yeah. But instead of that, let me just say that if you can use a okay, so generally you can get a pretty wild stuff, but if you things that you usually encounter in nature, like in heterotic string theory or something, are kind of not that general, but they are like they correspond to these guys being glued together in some sort of simpler way, and that produces the following class of examples. Let me call it an example. I will call it heterotic Courant algebroid. This will be kind of like a more global example, but I'm not saying that every transitive Courant algebra is actually this form, and that's not. In fact, that's not true. But it's a pretty general class anyway. And so basically it works as follows. So let G be a group with an invariant pairing on the algebra. So this is the same as before, but now I take a group as well with an invariant pairing onto the algebra, which I small g. And consider principal G bundle. Let this be a principal G bundle. And now, final thing to suppose nabla is a G connection. With a curvature. Again, if you consider this, and maybe let me put a star here again, like say that you won't need this in any sort of exam. With a curvature f and three form, not closed, just three form, such that satisfying one condition. GH is 1/2 F. Okay, so the data that I want to start with is I have a principal G bundle with a connection and a three form satisfying this thing, which some people call the anomaly cancellation equation. And then the claim is that the following is a Courant algebroid. Then the following is a Courant algebroid. And that's a kind of like a more global version, more global than the preceding example. So you take this one, and then you add the add G. So this is the should I call it? This is the associated bundle, right? Or adjoint bundle. Well, bundle associated with the adjoint bundle, let's call it. More specifically, this thing is the associated bundle corresponding to the representation, which is the adjoint representation of the linear algebra. So sort of like a version of that where kind of, like locally this thing looks like that, but globally there's some like interesting patching maybe. Okay, and the anchor and the pairing are the same, but the bracket is the kind of non-trivial thing, so we have to divide the bracket. Starts like this, and then it continues. Beta minus I y the alpha plus, and now there is like a connection, and then there is curvature contribution. So you see, this is kind of like a more complicated version of this bracket, where now there will be various terms appearing, sort of generalizing this twisting of by h. S, and there is NH as well. End of the one-form part. So there is three new terms that appear here essentially. And then there is the legal algebra related part, which looks like this. Okay. So you see that it's kind of like a global, maybe covariant version where stuff S and T were no longer functions, but now they are sections of some bundle, so we need to have a connection which acts on them. So that's why there is a connection, there's a connection here. So it's like kind of a more geometric version of that local picture.
And that equation BH is 1/2 of F.
That's important for the Jacobi identity to hold.
But in this heterotic supergravity, what kind of equation is this? Where does it
That's
come from?
called the anomaly constellation.
Yeah, but this info mechanism.
So it's a bit subtle there. So
So it's the functionality of the BH group and the one who construct from the curvature.
But is it? It's different than.
it's slightly it's okay. So the one you use in supergravity, the one that comes from string theory, that one has first of all the gate this bundle here. It has the Lorentz group kind of embedded in it. So you have like this thing contains the orthogonal group
and
how does it work?
and SO whatever.
Okay, you know what is it?
SO line and H group.
So that's contained in this logic.
Sorry?
So the space-time kind of.
Yeah, you have to embed it in this gate.
In this group, yeah.
So this kind of contains both that thing and the gate and the true gate group, and but it's kind of related to kind of, and all of this is like higher order. It's like alpha prime.
Because that's what I remember, that we were kind of mixing kind of three level and one.
Yes.
Like this green shows like a
Yes.
situation.
So if you're really interested in this heterotic in heterotic string theory, then you need to do, I mean, need to be careful about this in particular. So, yeah.
And before, like, when you...
I mean, I'll prime you high in the bracket, at least I can.
But like, if you don't consider this algebra, but you talked about also the type 2a to b, so that should be more similar to the usual one, which doesn't have the algebra, or you also need to... You know, you were also saying that this Courant algorithm that you were introducing before, without this...
Yeah, for type 2 you don't have this, then it's just exact, and
So
there is...
there you don't need to embed this kind of
No.
symmetric operator.
No, they're
But
not.
then the fields that you have in this type 2a or 2b supergravity, there are also differential forms than just like 2, 4, or different field strengths.
Yes.
So those you don't consider, or you can?
No,
These are Navier-Schwarz fields.
Yes.
But I mean, those things become they enter different. So they are spinners. They are like bispinners for the blah blah blah. So they are like really spinners for the Courant. So they enter naturally, but not in as part of the generalized metric, which is a thing I haven't talked about yet. But you can encode all the field content naturally. It's not just this kind of NSNS. But it really covers all the cases. And maybe just to finish this kind of general or like futuristic debate. So the claim here that if you want to describe like if you want to study like type 1 or heterotic supergravity with some arbitrary gauge group, let's say, then if you really look only at what is called the two derivative part of the action. So if you have string theory, then there's like all sorts of corrections there. But if you truncate it at the two derivative part of the action, then this is then you really recover this. Like then you have like a well-defined supergravity theory. It's like a classical field theory with some supersymmetry and everything. And this is the condition that you get there, because then you don't get the curvature square term, because that's higher order in derivatives. So the two derivative part of this heterotic string low energy effective action, which otherwise known as the supergravity thing, that one is well captured by this as it is. The problem is that if you want to really live this to string theory and you want to consider this kind of to make it consistent, then you need to carefully add these higher contributions. But if you really truncate at the two derivative level, then this gives a consistent theory, which however has a problem, I suppose, in quantization and everything. So you get some anomalies. So you need to be careful in adding stuff there. But as a classical field theory, this is fine. Does that make sense?
Yeah, I don't know that stuff that well, so.
But in string theory, you would have like plus R.
Yeah. But I'm not with confused whether this one is kind of classical or real, or if it is also including kind of a loop. Because this anomaly cancellation, I think that was kind of mixing, the classical like
Yes.
level and like one loop, no? So it cancelled
Yeah.
kind of one loops by adding a classical like 3 level.
Yeah, if you would quantize this, then you would run into problems. I think if you wouldn't add that R squared term there. But on the classical level, as far as classical field theory is concerned, then this is fine. It's fine in the sense that it is a theory which has like well-defined supersymmetry, and the supersymmetry actually like preserves the thing. So it's like there is not like up to stuff, but it's really like on the nose compatible with the, which is a very non-trivial statement. Still, that you can make it,
But here we do mathematics, so you don't care.
Also
It's mathematics.
okay, so end of remark for experts. Yeah. Okay. Okay. I think everyone is wasted. So let's say 10 minutes break. Okay. So. Okay. So, as I mentioned during the break, maybe, was that so next time we're going to do some gradient geometry, but before that I wanted to mention some parts in here that are kind of relevant and also useful because people don't talk about them that much. But before that I want to mention something about Lie algebroids anyway, since we already came this far, then everyone should know about Lie algebroids. If you know about Courant, you should know about Lie, which is simpler in a sense. So let's talk briefly about those and how you can get an example of those from Courant algebroids. Okay, so what is the definition? So Lie algebroid is a vector bundle. I will call it L for Lee. Equipped with further structure, just as Courant. There is bracket, most importantly, on the sections. It's bilinear with respect to real numbers. And a vector bundle map again called the anchor. And now the conditions are easier than for Courant, so you just want this thing is a Lie bracket. So it satisfies Jacobi as before, but you also want it to be anti-symmetric. And then you also want the same property as you had for Courant, or when you have two sections and you multiply one of them by functions. Then you want this. All u v sections of L and f a small function. Okay, so it's kind of like an easier cousin to Courant. So the bracket is anti-symmetric. That's kind of the point here. Okay, so what are the examples? What is the thing to have in mind? Like, what is this supposed to generalize? Well, one example is if you take M to be a point, then you have a bundle over a point, which is just a vector space, and you want that on sections that, which is just elements of the vector space, you want to have a bracket. So this gives just a Lie algebra. This is Lie algebra. Okay, so Lie algebra. Lie algebras are Lie algebroids over a point. So Lie algebra is sort of like generalization. If you have not just a point, but any point. And the other example on the other kind of end of the spectra is the tangent bundle. Okay, so this is equipped with the commutator of vector fields. It's this thing, the commutator of vector fields, which I before just completely written in this way. And the anchor is simply the identity. And in some sense, you can think of these as sort of interpolating or extrapolating between these two examples. And some, not really, but you know, these are two good examples to have in mind. And
So didn't you require anything about commutativity of the brackets?
yeah, it's a Lie bracket. So you want
Lie bracket.
so
Okay.
Jacobi and anti-symmetric.
Okay, it is anti-symmetric.
It is anti-symmetric.
Is
Yeah,
there something I didn't.
yeah. Sorry, I hidden it in here. Yeah.
So it's truly like fully degenerate, like regarding this question before, fully degenerate Courant algebroid with the pairing with
Yeah,
just
kind of. Yeah. In that sense. Yeah.
But what's the relation between the two, like between Lie algebroid and Courant?
So they are kind of disjoint. Or if the anchor is 0, then yeah. If the anchor is 0, then the axioms of Courant algebra tell you what it's about. More generally, okay. So then that's what I want to do. So you should treat them as like really two separate entities. It's I recommend doing that.
They meet in the heterotic bundle.
Sorry?
They meet in this heterotic bundle.
Well,
It's like a Lie algebroid of a principal bundle extended by one.
yeah. I mean, yeah, okay. Yeah, I will. Yeah. So let's do that. So proposition. I mean, this is a simpler case. So let's say if E over M is a regular Courant algebroid. Remember, this meant that regularity was the kernel of the vector has constant rank. Or image. Just the same. Okay, so if you have a regular algebroid, then you can construct a Lie algebroids as by simply modding out my image of the dual. This is a Lie algebroid. And I mean, yeah, this is, well, I mean, okay, I'm not, okay, the proof of this is kind of immediate. It's just the fact that the thing that made Courant not Lie was the fact that in Courant algebroid you have this condition. There's a curly D, but curly D, if you write what it is, it's D star of this guy. So if you mod out by image of this, then it means that all such things will be zero. So the bracket is anti-symmetric. And if the bracket is anti-symmetric, it satisfies Jacobi because it was a Courant algebra. So this holds, and this condition also. So everything. Yeah. The only thing really, the only real thing is to make the bracket anti-symmetric, and that's actually precisely by modding out by this guy. So proof consists in noting that the same thing occurs here and here. You kill the bad stuff, and what is remaining is good. Okay, as an example, so if you take, what happens if you take the exact Courant algebra? If you take this ECA, what do you get from this? Tm. So this thing was, as a bundle, it was Tm plus T star m, and the anchor map was the projection here, which means that dually this map, this is the rho star, dually this thing is just the injection of like P star m gets mapped to the second factor. And if you model that out, you get with Tm. This thing produces Tm. So that's precisely that example. Okay, so
Sorry, this is also in this. So, how does the inner, like the pairing, end up being on this? I mean, can we induce a pairing on this,
no,
on this quotient, or is it just
no,
always? In this example, it's zero, right? Because it kind of degenerates. But in general,
no, I mean, no. So here you're only killing part of the thing. So, but the claim is that the pairing in general just doesn't descend.
it doesn't descend.
No, it doesn't. Yeah. So I mean, yeah, it will be a Lie algebra. Okay. I mean, yeah, in particular, it will be a Lie algebra in this thing. I mean, oh, okay, sorry.
No, it's
Yeah.
just a Lie algebra. I mean,
It's just a Lie
it
algebra.
doesn't have
There is no
also
pairing.
pairing.
Yeah. It doesn't.
Okay. Thanks.
Very good. Okay. So then maybe to finish this part, let me give a thing that we define a Dirac structure, generalized complex structure, just mimicking what we did before. So fix a Courant algebroid. And then we say that a Dirac structure or a generalized complex structure, so I will write both of them at once. Generalized complex structure is a Lagrangian, I will define it like this, Lagrangian involutive subbundle of, in the first case of the Courant algebroid, and in the second case of the complexification of that. Okay, I mean, I'm putting them together, which is a little bit, sorry, and in the second case also, okay, this is in the, how should I do this? No, that's bad. in the second case, you also require that someone will L of this thing, and in the second case, you require this is 0. Sorry for that. Maybe we should have written these two definitions really. So Dirac structure is a Lagrangian equality sub-bundle of this guy. And generalized complex structure is a Lagrangian equality sub-bundle of this one. Yeah, I mean, it's a little bit of a cheating putting them together, because in the first case, there is no complex numbers. This is just a smooth sub-bundle, like a real sub-bundle. In the second case, I really want it to be complex. So, but I'm hiding that. Should I write it? Okay. If this is confusing, then just look at the definition we had before. It's the same definition. It's just that instead of having the standard algebroid derivative in general. But okay, so then one implication from this is that L in both cases is a Lie algebroid. Simply for the reason that it's Lagrangian, so it's isotropic. So the pairing of it vanishes, and if the pairing vanishes, then the right hand side of this guy is 0. Okay, so the bracket on these sections is actually anti-symmetric. So it's a Lie bracket. Hence it's a Lie algebroid. Okay, so this is another way how to get Lie algebroids. Okay, that finishes this part. Any questions for that? I apologize for being a little bit messy at some point. Okay, you can ask later still. So, okay, so the last part in this section, so before we go to graded geometry, which I know many people are looking forward, including myself. Last part is this thing that I feel that is often not emphasized too much. So let me do it here properly. So let me call this part generalized Lie derivative. And Courant algebroid automorphisms. And let me start easily, so let me just say what this generalized Lie derivative is. So definition, fix a Courant algebroid. And then for any section U, we define the generalized Lie derivative I will call it curly L U. And this thing will be something that in the first instance this will take some tensors in E. So a bunch of E, it's a tensor product of a bunch of E's, let's say n of them, and creates again tensor of the same type. So it's this defined by as follows. So we define this thing by, and now let me list how this works on the lowest order thing. So if we act on a function, so on functions, which would mean n is 0, this thing is simply defined using the anchor map. Okay, so I take a derivative of a function. So if I would take another section, so if this is n equal 1, okay, so this is the n equal 0. Now the n equal 1 case. In the n equal 1 case, we have a section, some section B, and we define the Lie derivative, the generalized Lie derivative to be simply the bracket. Okay, so it's kind of the analog of how you construct ordinary Lie derivative if you don't want to talk about flows, but you want to talk about commutators of vector fields and vector fields acting on functions. So this is kind of what you would have in ordinary geometry. And then by Leibniz on higher. Okay, so here you have a little bit to check that it actually is consistent. But you know what I mean, like, so if you would have like, you require that if you would have two tensors, let's say t and u, then you want that this is LU of t, u plus t tensor u is here, t and t prime. That's the end. And then, okay, of course, I have to a little bit to prove that it actually, that this last line gives you a consistent definition, that this is consistent. If you take your big tensor and split it in multiple ways, you have to show that it gives literally the same thing. But it's not difficult, so let me phrase it as a remark. First part of the remark is that this is well defined. Because of the following fact, or let's say due to the one axiom that we had before. And the axiom was that if you take, you multiply the second slot, the section by a function, then it goes out, and then there is a second term where this gets multiplied. And now if you write it in the Lie algebra language, then what this thing tells you, the left hand side is the generalized Lie derivative acting on this product. This thing is the f times generalized Lie derivative acting on v, and this thing is the generalized Lie derivative acting on f, and then multiplied by v. So you see that you get Leibniz for this particular case. So you multiply functions with sections of e, and you can show that this is enough for this thing about to be well defined on any tensors. But you know, on ordinary. Okay, right. So if you work in ordinary geometry, when you define Lie derivative in this way, then you also need to say how it acts when it acts on duals. You know, like because tensors in ordinary geometry, they are sections of the tangent bundle, but also they can have some. You know, it's a tensor product of bunch of tangent spaces, but also you can have cotangent spaces. And also more generally in ordinary geometry. I mean, when I say ordinary geometry, I just mean differential geometry. So if you normally define a Lie derivative, then you talk about flows. So Lie derivative is not just something that acts on tensors, but it can act on more general objects. Anything that you can use a flow to, to act on. Like you can do half densities, maybe spinors in some lucky cases. So with a little bit more than this.
So it is in some way compatible with all the Courant algebroid operations, right?
Yes. Yes, it is. So yeah, precisely. So most of this Courant algebroid axioms, what they tell you is that this thing actually preserves the pairing and it preserves the bracket. That's two of the axioms even.
Mm-hmm.
So you can phrase them in this language. You can say that this generalized Lie derivative preserves that. So, so what is Lie derivative on some psi for psi being an element of the dual, I mean, a section of the dual? So, well, you can have, you can think of it in two ways. So either use the fact that we know what this thing is. I mean, sorry, we know, we can identify these two things using the pairing, and then we just use the Lie derivative on sections. That's one way. The other way is that you use the thing that you know in ordinary geometry, that you define action on one forms by the fact that if you pair them with a section, then you want that this thing is psi, sorry, this is u acting on, in this case, rho of u, or Lie derivative of u, acting on psi of v minus the action here, minus psi on Lie derivative of u on v. This is how we define Lie derivative on covectors in one form fields in ordinary geometry. But now, which one do you use? Well, it doesn't matter. It's the same. Okay, so they are the same here. And why? Well, simply because in a Courant algebroid we had that one axiom which tells you that the pairing is preserved by the brackets. So if you break it down, it tells you that those things are the same. Okay, so this is not terribly surprising. It's because, yeah. Okay. So this is the reason why I didn't include E star here, because it's really just the same as E in a Courant algebroid. Okay. Any questions for that? Well, if not, then let's do the final part, which is now now I want to make something similar to the picture of the flows, and this is particularly useful if you want to work with.
It is essentially also like inner pairing.
Sorry?
You can have Lie derivative. You can have also now inner pairing, because you just pair one component, like, insert it into the. So you have like L and iota.
Mm-hmm. Okay.
So do you have like the Cartan calculus or something like that?
There's no D, right?
There is no D, yeah, but yeah, all you is make up something.
Yeah, okay, so it's the other way around, right? If you have D and I,
Yeah.
So, right, yeah, thanks.
There is no way to make up the D.
No, there should be.
There's D on functions, but otherwise, right?
Yeah,
So you don't understand.
I think so. I know Lie algebroids it works, but not here. Good, thanks. Okay, so now let's talk about the last thing before going into the basic geometry, and that's the analog of flows and how to generalize this notion on other classes of objects such as spinors and other stuff that you're interested in supergravity or in other contexts. So okay, let's do it as follows. So let this be a vector bundle. So let's relax. Let's forget about most of the structure. Let's say this is a vector bundle, and phi is a vector bundle isomorphism. Covering the map, I will call it phi bar on the base. This is actually a diffeomorphism. So picture really here you have a bundle. And this map having a vector bundle isomorphism covering such a thing, it means that you are here and you get sent somewhere, you are somewhere else, you get sent somewhere else, but the fiber should be preserved. So this is really sending all of this fiber into this fiber. So there is really a map on the base, which is this fiber. And here we have phi. So before we saw this in the case when phi bar was an identity, but more generally you can see it like this. And then, okay, now suppose that we have a section. So for you, a section of this bundle, we define a pullback by phi in this seemingly strange way. Okay, this is the section of E again. Okay, so this looks a bit strange. Normally you would just want to, why do I have phi on both sides? But if you think about it, then it's kind of the only reasonable definition. So, again, picture. But the problem is that a section is required to be something that goes horizontally up. So if you are sitting here, it should land in the fiber above. Okay, so let's say I'm at this point, and okay, so let's say this is the picture of U. Okay, so this is U, and now I have a this green map, this isomorphism, and let me drop why this is meaningful. Okay, so let's say I'm at this point, and I want to calculate what is phi star of U at that point. So how do I do that? First, I go by the map on the base, so I get sent somewhere here. Then I look at U up there, so I land up in some point here. This is U. But I want to have something that's sitting above the same point. So, well, then I use the map on the total space to come back. So there's like a map, I don't know, like this, and I go here.
So without this inverse, you would get a section of an isomorphic bundle.
Yes, that's right. That's right. Yes. Yeah. That's it. Thank you. Maybe that's a better way to say that. Or alternatively, what you can say is that. Well, okay, yeah. Well, anyway. Okay. This is what it is. Just keep in mind that there is these two phis. It is a natural thing to do in a sense. Okay, and then I will call the group of automorphisms. It's called such automorphisms. I will call it out E. And now an infinitesimal counterpart to that. Okay, so an infinitesimal no, sorry. Before going that, let me define the Courant algebroid automorphism. So, a Courant algebroid automorphism Courant algebroid automorphism is a vector bundle automorphism so Courant algebroid automorphism of a Courant algebroid, which let's call it E over M. So this is a vector bundle automorphism phi of E covering some map on the base, so the same set as above, covering a diffeomorphism phi bar of M. Now I require that the following holds, that the structures are compatible. And if you write it down, what it means is that if you pull back two sections, should be the same as if you pull back, if you calculate, if you pull back two sections and then you calculate the pairing, it should be the same as calculating the pairing and then pulling back the function that you get. It's a function on the base, so you need to use the base map here, 5 bar. That's one thing. Yeah, then you want to have that for brackets. You have the same thing. Maybe I should be swapping left and right. Sorry for that. Okay, so it's a kind of obvious thing. And for the anchor map, you pull back a section, you get a section, then you use the anchor map, and then, well, I want this to relate this to row of u, and the only kind of reasonable way is then I have to push it forward by the base map. And okay, and the group of automorphisms will be called out E. Yeah, that definition out there was supposed to come here, so well, we can use it in both instances. Okay, so the generalized is the automorphisms that we had before, which were over the identity. Now the final part here is that let's define an infinitesimal. So an infinitesimal automorphism, infinitesimal Courant algebroid automorphism of a Courant algebroid is a vector field. Which is a vector field on the total space. Okay, so it's a bunch of arrows, but not down, but up. Whose flow is given by, or whose flow is how should I, like I want to, flow is given by Courant algebroid automorphisms. So if I integrate that, so if I integrate that bunch of vector fields, then I should get a diffeomorphisms of the total space, and those should be of this type above. So they should be covering the diffeomorphism at the bottom. They should preserve the linear structure on the fibers. So that's all hidden in here, and it should preserve all the structure.
Right, so this is non-trivial, right? For manifolds, you integrate, you take the flow of any vector field, it's a good isomorphism, diffeomorphism.
Well, no. In general, I mean, if it's compact, then yes. If it's not compact, there is vector fields.
Or if it is complete.
Yeah, complete. Okay.
Right. So here, technically, okay. Thank you. I was okay. Yeah. So if I want to be technically correct here, then here this should be. I was discussing this yesterday with. Anyway, so I was preparing for this question. So properly one should take local flows if you so properly. So if M is, let's say, non-compact, if it's compact, then it turns out that this is fine, even.
Every field is complete.
I mean, on the face, but here you have like the fibers are non-compact.
But if the field is complete on the total space, then.
Well, yeah, no, but well, okay. So if the okay, I mean, you can imagine some crazy field up there which won't integrate into anything, but that will okay. Let me do the other way around.
Yeah, but since you have vector bubbles, they are never compact, no? So you can at most assume no magnitude base, for example. You cannot, the fibers are always non-compact, so
Yes.
that would be useless.
Yeah, no, I realize that, but I'm saying like if that vector field is supposed to generate something that's a linear and that really preserves the linear structure on the fibers, then it needs to be No, okay, yeah. So okay. So if even if okay. So the way to read this is that you want that this integrates. Let's say the compact case first. If if the base is compact, then part of the definition is that you assume that by this I mean that first of all there is a flow, it exists at all times, and it gives you this. If it's non-compact, then you require that to be instead of talking about flow, you want this to be a local flow, but local in a sense on M. So even if this is kind of like yeah, so you want to restrict to some local open sets on the base and yeah. So the kind of the punchline, like the keyword here is that the fibers are not compact, but it kind of it's okay here because they are okay. Yeah, let me just write it like this. If this is compact, then you just require part of this that it integrates. If it's not compact, then you still require that this integrates in some local sense on M.
So my question was, yeah, so I was thinking locally, but my question was more on the fact that it's an automorphism of the Courant algebroid. So it preserves the pairing and the... So is that automatic also here, or is this
No, that's a very strong question. Yeah. So this the fact that it integrates that yes, I mean the fact that it integrates that's like pretty general, but you want that it integrates to Courant algebroid automorphism, so they need to be this satisfying all these three concepts. That's a very strong question. Yeah, sorry, I misunderstood, but anyway, I wanted to say that.
Do you have something for those which don't integrate?
Sorry?
Whether you have the name for those which don't integrate?
No.
But preserve infinitesimally the structure, because you can take the, just linearize the equation in phi you have about.
Right. Oh yeah. Okay.
We have it in terms of vector fields, right?
Right. So you can define something like so you would define some sort of differential.
The curve is 1 plus the vector field, and you expand, like first order.
Right.
These equations, you get something, but they don't need, then you forget it how you got it. That would be your definition of something. So
Right.
it's still kind of infinitesimal.
Yeah. Okay, so you can maybe but then it would. But I wanted, for some reason, I wanted to be really vector fields living here. So I don't want it to be some abstract thing that takes a section and produces a section, but I want it to be realized by a vector field. I didn't see why. Maybe I don't have a good reason actually, but I agree. So you can kind of take a derivative of these things and come up with some sort of condition on, and you can phrase it in terms of sections, and you can kind of don't worry about this, and right, you can do that. I'm not going in that direction because I'm prepared, but yeah.
But you want whatever automorphism, so to preserve the linear structure on fibers, no?
Yes, that's part
so
of it.
because of that, you should not worry about.
It's all hidden.
Yeah, so you should not. Then in the end, you will not worry about this non-compactness in the direction, no? Because there it's clear that the vector fields, are acting linearly on the fibers, that they will be complete.
Yes. That's yes.
And on the base direction, you can assume locally the flow is kind of can be exponentiated.
Right. Yeah, precisely. Yeah, I was just. The reason I was worried for a moment was that like here you want to go in a different, like in the opposite direction. Like you want to have a start with a vector field, and you want to say that the vector field is an automorphism, but that's what puzzled me for a moment, because then in principle it cannot integrate, but then if it doesn't integrate, then it should not be a Courant algebroid automorphism. So it works, as you say.
Yeah. I mean, in usual manifolds, every field kind of it exponentiates on small neighborhood, no?
Yeah.
And here you cannot use it because of this bidirectional, but since you want to preserve the linear structure, it cannot do any,
Yeah, exactly. Yeah. So because that kind of.
So let's say your read derivative would be kind of infinitesimal, right? Would be an infinitesimal automorphism.
Right, but linear uses. Okay. Yeah. So the whole.
It's in sections.
So my whole problem was that that like you want to preserve the linear structures of the fibers, which was kind of, and I don't know a better way to say than using a flow, like, so I will need to integrate it in some way. But then if you have something that's, but anyway, this definition is correct. It's just
Paolo said it.
yeah.
But like preserving the linear structure here, you are assuming it. So even if you write the infinitesimal version, you will still assume it. It's kind of, you are assuming it anyways. So you could
Yeah,
just
but
assume
the
it
first assumption is that this integrates to a flow, and then that flow, the second assumption, needs to preserve the fibers and preserve the structure. So it goes in those stages. Like first it should integrate.
Yeah, but if you wrote infinitesimal version of these equations, I guess do the same thing, and you would not need to worry about this exponentiation.
Yes, but yes, but they would need to. Okay, like, but what would you mean by infinitesimal version of these equations? Like, you would say that like you take a derivative and then you have some sort of operator on sections. So you can phrase it in that way, and then you don't worry about it. Yeah, that I agree. But like, I didn't want to phrase it as an operator that acts on sections. I wanted to phrase it as a vector field on dot space. Again, for no reason. Obvious. Okay, so don't worry, it should be correct. It's just that, yeah. Okay. Okay. Well, then okay. Then there's two last propositions that I wanted to end up with. Okay, let's go on. The main proposition. Why I was built doing all of this is that if you fix a Courant algebroid, then for every section of E, there exists a unique I didn't write it. Okay, so the group of those are the Lie algebra. Sorry, part of the definition above. So the Lie algebra of infinitesimal automorphisms will be denoted. It will be called small out. Okay, so now I want to say claim that for every section here there exists a unique infinitesimal automorphism. Satisfying the two conditions such that Z of U covers the vector field rho of U. Okay, so we have an anchor, we know how to turn a section into a vector field, and I want that this thing is a vector field covering, like that projects down to this. And the second condition generates the bracket in the following sense. That if I take the flow for some time t of this vector field, and then I pull back some section, let's say, I don't know, V. So I want to mimic the Lie derivative essentially, and then I take the derivative of that at time equals 0, and this thing should be U of V, U bracket V. Okay, because remember this pullback was defined up there. Pullback by one of these automorphisms is a thing that takes a section and produces a section. So that's what I mean here. I'm pulling back section, getting a section, and I want it to be this.
So are you saying that these are more general than just taking the bracket with some kind of...
Yes. Yeah, they are slightly more. Well, not depends on the case. It depends on the depends on the Courant algebroid. But in the exact one, I think they are like almost. There is a little bit more. But in general, it can be much more. You can, for instance, you can imagine a Courant algebroid which is which has 0 anchor and 0 bracket. So that would be just like a bunch of abelian layers, like essentially a bunch of some. It will be a vector bundle with a inner product, no more. And then there is lots and lots of automorphisms that you can just flow here and there and whatever. But none of them will come from a bracket because bracket is 0. So if you take such degenerate cases, then yeah, you can yeah. So in principle, they are disjoint. No, not disjoint. Sorry, this is included, but there can be much more of those. And as proof, let me give you a sketch of how you can actually construct this. It's a picture I like to draw. So again, maybe let me call it proposition with a star because again, this is something that's not it's not definitely not a common knowledge, or at least people don't talk about it that way. Okay, so let's say that we have fix u section and fix a point, say E in E. Okay, so we have our more picture. So we have our section, and now we want to create a vector field. And now let's ask, like, what does a vector field look like? Let's say at this point. This is point E. And so what I want to do is that I pick any auxiliary section B passing through that point. Okay, so remember the picture. I pick an auxiliary section, I call it V. In the end, I want to claim that it's independent of it, but for now, we'll just pick as auxiliary section. And what do? I look at the fiber here. This corresponds to a point here. And then here, this is my data, U and E. I use the anchor to create a vector field. So I get in particular, I get a vector here, which is rho U. And let me here, okay, you can make it more geometry, but let me kind of work with, let's say I pick some coordinates or something, and let me just say that this vector is epsilon times rho of U, so it sounds like small enough direction. And then what I do is that I look at the new section, which looks like this. Which I will call V minus epsilon UV. Okay, so I have E and U and E, but I also picked some auxiliary sections, so I can construct this new section. It is a section that looks like this. And then what I do is that I look at the fiber above, and I pick this point. And I claim that this vector that we get in this way, this is epsilon times Z of U. And then the claim, and in this way I get if as I said epsilon to 0, then I really get some tangent vector. I don't, so far is it some coordinate neighborhood or something, but if I set epsilon to 0, then I really get like a tangent vector. And the claim is that this vector is independent of the choice of V. Meaning that if I take a different section which still passes through the same point, then of course this construction will change, but it will change in two places and they will cancel each other. So the result is well defined. And kind of because of the construction, one should be able to check that those conditions above hold. For instance, we immediately see that if I project this down, then I get a row of U. Okay, but even but even knowing the proof, it's kind of the important thing is to realize that there is like a natural for each section you have this natural automorphism of this thing, which is not vertical, it really flows with the, it moves on the base. And this is the thing that you can use to kind of, this is a thing that extends the generalized derivative Because here we see that it acts, it's something that generates the brackets, this guy. So we see that it contains the information about it contains information about the row view, but it also tells you how the bracket is generated. So we can extract from this linear derivative on functions and sections. But we can do much more. If you define some spinners, which we might do later on, let's see, then in this way you also have natural transformations of those. So yeah. So this is kind of a more general picture. That you really have this bundle, which is an automorphism of this bundle, and all the associated structures that you can associate to this, they are kind of flowing with it. That's a bit of an abstract statement, but yeah. But it all just follows from this thing. Okay, and just a small aside, like the final proposition about this object is that it satisfies the thing that one would expect. So this map from this guy to the automorphisms of E, which was this U gets sent to Z of U. So this is R linear. And preserves the brackets. Okay, so preserving brackets means that Z of U bracket B, or this is the bracket in the Courant algebroid. This is the same as bracket of Z of U and Z of V, which is this is the bracket of vector fields and total space, or the bracket in automorphisms. Same thing. And this is the bracket in V.
Sorry, I'm good lost in your picture. So you considering you actually define Z by constructing the section, the green one, minus the bracket, and then you define ZU by
Epsilon ZU to be this vector.
Also express it in the point shifted by epsilon rho U.
Yes. So you can do it more. Oh no. Right. Let me lock this thing. Okay. Stop moving. Okay. Okay. This is essentially all that I wanted to cover in the Courant algebroid section. Next time we do something completely different, sort of more general in graded geometry. But maybe just so this was kind of a bit sketchy because I was using symbols like the epsilon times vector to denote the point and everything. But you can do it like kind of if you want to be more formal, then you can say that for instance you would say that here instead you take some curve, it's the gamma bar in M, such that gamma bar at 0 is this point, M, stand here, and gamma bar dot at 0 is a roll view. Yes. You take any such curve. Then you take oh, maybe that's the only thing you need. Right, and then you take again a family of sections. So you will have like some, I don't know, V of epsilon, V of t. You would take it to be V minus t times this thing. So you promote all of these families. So you will have like you would have a family of sections which start at V, but then they go further. And then I would say that generally you just look at the pre-image of, or you look at the value of this at the point gamma. So you look at Vt at gamma bar t, and that should give you kind of abstractly speaking this point here. And then you would take like the derivative of that.
Okay.
And that should give it. Yeah, that's really what I meant by this. If you want to make it formal.
Okay.
Yeah. Hopefully that's okay. Yeah. Okay. And but now okay, here you have to check not independence of this gamma bar, but actually you can choose different gamma bar and get the same stuff. And the independence of B. Okay, so that's yeah. I realized that maybe today's topic was kind of more like a I wanted to kind of, since I already built up all this framework, and it will be kind of pity not to mention this because I find this incredibly useful in many ways. But yeah, this was a start, so I mean, don't worry if that was. Okay, like okay, it went a little bit off the hook, so. But okay, hopefully this was still helpful. Maybe to people who work in the subject. Maybe there is still a better way how to present it. I suspect that might be maybe an even easier way to imagine how these things work. But okay, so yeah, and there is many other topics in the Courant algebroid business because that's a kind of rich topic these days. You can do reductions, talk about Dirac operators, applications to generalized Riemann geometry, and maybe T-dualities and string theory. And we will sort of cover these things, or at least most of them, but in a different way. So we will kind of seize this as this, like we will stop here. Next time we will instead adopt the graded viewpoint, which will be very different, although in some sense equivalent, and in some sense also more similar. But to truly appreciate the simplicity of that framework, it's useful to see how complicated stuff can be formulated in the vector bundle language. Let's say that's the reason that I'm. No, I mean, okay, this is useful in general. Also for other purposes. Okay, well, thanks.